This is the setup for the first experiment, a measurement of numerical aperture of an optical fiber. First of all, you have to obey safety rules. That means it doesn't matter whether you use a laser pointer as a light source or a green laser here. You never should direct it in such a way that anybody looks directly in the beam, as well as nobody looks directly into the light going out of the fiber. So, as I said, here you have this light source. So this is a laser, or you can use this laser pointer also. These are some holders that hold this fiber, and this is that plastic fiber. As you see, it's 1 millimeter thick optical fiber, which is directed on a screen. As a screen, you can use either a screen which is measured in millimeters. So here you directly, if you direct here, can measure the diameter of that spot of an optical fiber, or if you use just a white paper screen, you can use a ruler to measure this diameter and to measure the distance of this fiber from the screen in order to find that sine theta. Now I will turn the light off, and you will see how this spot looks like, so you really can measure its diameter pretty well. So this was our first experiment. The second experiment is the attenuation of the optical fiber. So let's go to the second experiment. This is our second experiment, measurement of attenuation in optical fibers. And here you see a coil of optical fiber, several tens of meters long. And this fiber is illuminated by a laser. You can see it. Of course, if you don't have such an expensive laser, you just may use a laser pointer to illuminate it. And then the other end of this fiber is directed towards a photodetector, and this photodetector is connected to a power meter, so you directly measure this power here. Then, after you measure this power, you cut off a piece of this fiber, say 1 meter long, not disturbing the coupling to the laser, and measure the power of light going out of this short segment of fiber again, and then taking the ratio of the power measured from the long fiber to the power measured from the short fiber, taking that common logarithm, you can find attenuation coefficient in decibels, as is shown in the slide, in the corresponding slide. So this is our second experiment. And now I will go to the next one. Here we are considering experiment number 3, making a fiber optic coupler. What you see here is exactly that. I took the fiber we used last time for attenuation measurement. I twisted 2 pieces together, and then I used a heat gun and heated this twisted portion. So they melted to each other. And here I received this coupler. You can see how it couples out. If I send my laser pointer to just one port, you see that light goes from both sides of that. And especially it will be visible if I turn my light off. So let's do that. Do you see? So it really couples light all together. Now let's go to another. Here I have 1x3 coupler. Again, a little bit thicker fiber is coupled similar way together. You can see 3 lights outgoing from there. And here I have 1 photodetector connected to this power meter, and the second photodetector connected to the second power meter. Of course, you may use 1 power meter and just change the position of photodetector. And you see that both give you readings of a light that was coupled from this fiber and this laser to the other 3 fibers. Of course, again, you may use a laser pointer as an illuminating source and any photodetector. I will turn light off now, so you will see everything better, how everything is coupled. So we go now to our final experiment. This is our final experiment, wavelength multiplexing. Here you see the fiber coupler that I showed you made from 1mm fibers. And here I have two light sources, a green and a red laser pointer. And when I illuminate this fiber, you can see that these wavelengths are combined here. So here I use two different color laser pointers. Of course, you can use light emitting diodes, LEDs, as light sources. And now I show you the complete setup. If you look here at the table, you see again two light sources, one a red light source, the other green light source. They are connected to two fibers that are coupled together into the outgoing fiber. If you look at the output of that outgoing fiber, you definitely see that light is yellowish, which is a combination of the green and red light. So they are multiplexed. And here I have a diffraction grating. So when you look through the diffraction grating, you can see that really you have both colors there. You have the central bright spot, which is yellow, and red and green separated. So you can take a look from the other side through the diffraction grating.